There's one scenario in kinematics that we use a lot, and that's when we assume over an interval of time that the acceleration is constant. Now, this might not actually be the case in a particular thing you're modeling, but often it's close to being true, and the results we get from this setup can actually say something helpful about what's actually going on. So some common scenarios that might use this kind of assumption would be free fall of an object, or a car accelerating from rest, or a predator chasing some prey. Kind of the possibilities are fairly endless. If it moves, then there's a reasonable chance we can use this as a first approximation to what's going on. Now, why is this constant acceleration approximation so useful? Well, what it means is that it leads to a set of equations that relate acceleration, velocities, and displacements together that kind of bypasses this need to draw graphs about what's going on. We can relate these things directly using equations, and that means we can perform some calculations that can actually give us some numerical results quite readily. So the equations that we're going to figure out today are known as the kinematic equations. Okay, so using the kinematic equations can result in quite a lot of symbol manipulation. So in this video, we're going to be fairly careful when we're rearranging equations and things to kind of explain how we're doing that and not sort of rush through them. So kia ora koutou, I'm Richard Brown, one of the lecturers of biophysical principles. So here's the plan. We're going to start assuming this constant acceleration by looking at an acceleration time graph, and we're going to see if we can work backwards using our graphical insight from the last couple of videos to figure out equations for velocity and for displacement. So let's start with that acceleration time graph. We'll mark on Ti and Tf as usual, and we're going to put in our acceleration as a constant a, which just gives us a flat line. Now we can start to put our work from last lesson into practice. We know that we can get the change in velocity delta v from our acceleration time graph by taking that signed area, remember the area above or below the axis. So for us that means we're going to have delta v as the height times the base of this rectangle here, which will just be a times delta t. Now, if the acceleration is negative, this equation will automatically produce a negative area, so it's going to work in both situations. So this is our first kinematic equation. Now, it's more commonly expressed by replacing delta v with vf minus vi and rearranging it. So that would be vf minus vi is a delta t, and if I just add vi to both sides, that will give me vf equals vi plus a delta t. Okay, so in this equation, it relates four kinematic quantities, that's Vf, Vi, A, and delta t, to one another. If you know three of those, you could use that equation to find the other one. Okay, now let's move on to velocity. So assuming that we know our initial velocity, okay, our acceleration graph doesn't tell us anything about that, just about the change in it, we can now draw a velocity time graph. So we know that constant acceleration gives us a straight line velocity graph. So ours will be a straight line graph that goes through Ti-Vi and Tf-Vf. So now we can work out our displacement from this graph as the area between this graph and the axis. And again, these negative areas, don't worry about those, they will be taken into account automatically. You can sort of double check this yourself later on. So that will be delta x will therefore be the area of this rectangle plus the area of the triangle on top of it. So that'll be the height of the rectangle times the base plus half the height of the triangle times its base, which is the same. So that will be Vi delta t plus 1/2 delta v delta t. That's the height of that triangle is delta v. Now, once again, we're going to replace the delta v with the one we computed earlier. That was delta v is a delta t. And if we substitute that in, we'll get delta x is equal to Vi delta t plus 1/2 of a times delta t squared. This is our second kinematic equation, and this time it relates the four quantities delta x, Vi, delta t, and a. Now we got this by substituting one equation into another. Now we're not going to go into all the details, but it's a set of 5 equations that each can be formed in this kind of way that are commonly collectively known as the kinematic equations. If you're looking for a bit of a challenge, you can see if you can figure all of them out in a similar way to what we just did. So the 5 equations are Vf equals Vi plus a delta t, our first one. delta x is vi plus half a delta t squared. That was our second one. Then vf squared equals vi squared plus 2a delta x. That's the third one. Delta x is a half times vi plus vf times delta t. And finally, we've got delta x is vf delta t minus 1/2 a delta t squared. Okay, so these 5 equations, they relate the 5 kinematic quantities that we care about, vf, vi, a, delta x, and delta t, to each other in various ways. So each of these equations contains 4 of those quantities. So if you know any 3 of them and you want to know the 4th, you just need to choose the right equation to solve for your missing quantity, and all combinations of 4 out of the 5 are represented by one of these equations. For example, if I know vf, vi, delta x, and I want delta t, I can use the 4th equation to solve for delta t. Now, one little note, it's usually best to avoid using the equations with delta t squared to calculate delta t, not for any hugely important reason, but solving these ones does involve using the quadratic formula, and usually you have to eliminate one of the 2 solutions that comes out from doing this. So it's usually a little bit simpler to find the other missing quantity first, and then to use one of the other equations to get delta t. Okay, now the best way to sort of understand these things is to go straight into a sort of physical example, and we'll show the kinds of ways that you're going to use kinematics in this example here. All right, so in our example, we have a swan, and the swan gets airborne by flapping its wings and running quickly over the top of the water. The swan must reach a speed of 8 meters per second to take off, and it accelerates from rest at an average rate of 0.40 meters per second squared. The 2 questions are, number 1, how far will it travel before becoming airborne? And number 2, how long does it take to become airborne? All right, so this is a good and proper physics word problem. So first thing we're going to do is we're going to look for some clues that we are actually allowed to use the kinematic equations here. So we're told an average acceleration of 0.4 meters per second squared over an interval. So we're just going to assume that our acceleration is constant, which enables us to use the kinematic equations. So the next thing to do is to figure out what it is that we actually know. We haven't been told anything about positive and negative directions in this problem, and that's quite normal. So we need to set those up for ourselves. So let's assume that the swan starts at x equals 0. I mean, that seems like a logical choice, at time 0, and that it accelerates in the positive direction in a straight line. Okay, so we're given the acceleration is a equals 0.40 meters per second. And we also know the takeoff speed, that's going to be our final velocity, vf, is going to be plus 8 meters per second. It's going to be the same direction as that acceleration. So we've got a, we've got vf. What else can we get? Well, we're also told that it accelerates from rest. That means that when it starts, it's not moving, so its initial velocity is going to be vi equals 0. Right, now we've got enough information to move on and answer these questions. So for question 1, we know vf, vi, and a, and what we want to know is how far it will travel. So the distance traveled is just going to be our displacement, delta x. So we know 3 quantities, and we want 1 quantity, so we should be able to use our kinematic equations to do this. So looking at our list of equations, we can see that this formula should work for us because it contains the 4 things that we're interested in. Vf squared equals vi squared plus 2a delta x. Now it's very tempting to just stick the numbers straight in at this point before solving for delta x, but it's usually a better idea to rearrange the equations first and to put the numbers in at the end. For a simple equation like this one, it doesn't really make much difference, but it's a really good habit to get into because things can get quite messy if you don't do this for more complex problems. Also, if you were to go and round any of your calculations, if you stuck them straight in, then as you go through your workings, you can end up accumulating rounding errors so that your overall result can actually end up quite a long way out. Okay, so anyway, so let's try and rearrange our equation for delta x. So I'll first write the equation the other way around, just because I want my delta x on the left-hand side. So it'll be vi squared plus 2a delta x is going to equal vf squared. Now my goal is to isolate delta x, so I'm going to subtract off that vi squared term from both sides. Remember with equations, what I do to one side, I must also do to the other. So this will give me 2a delta x, the plus vi squared and the minus vi squared will cancel off, equals Vf squared minus Vi squared. Now finally, to get delta x by itself, we'll need to divide both sides of the equation by 2a. Remember that the division happens to the whole right-hand side, and so it ends up being delta x equals Vf squared minus Vi squared, all divided by 2a. Now's the point where we can go and put this in our calculator, and we'll get delta x is 8 squared, or 8.0 squared, minus 0 squared, all divided by 2 times 0.40, and that comes out to 80 meters for our displacement. So the Swan will travel 80 meters before it gets airborne. All right, the second part was how long does it take for the Swan to get airborne? So to find out how long it takes, we're just trying to find delta t. Now we have all of the other quantities, so we should just go for the simplest formula. I'm going to use this one, Vf equals Vi plus A delta t. So maybe pause the video and see if you can rearrange this one for yourself before you go on. But what I'm going to do is I'm going to do the same kind of procedure as before. So again, the first step is going to just be to write it the other way around, so I get the thing I want on the left-hand side. So it's going to be Vi plus A delta t is equal to Vf. I want delta t, so I want to get rid of the Vi from the left, and so I'll subtract Vi from each side. So I'll get A delta t, the Vi's will cancel on the left, is equal to Vf minus Vi. Finally, I'll divide through by A, and I'll get delta t is Vf minus Vi, all divided by A. Make sure you divide the whole fraction by A, not just the Vi piece or the Vf piece. So now we're at the point where we can put our numbers in again. So I'll get 8.0 minus 0 on top, divided by 0.40, which gives me 20 seconds for our Swan to get airborne. Now the last sensible step is to take all of your life experience with swans and lakes and to check that what we came up with sounds at least vaguely plausible. So 80 meters-ish to take off and 20 seconds, yeah, sure, it kind of sounds like the right kind of ballpark. It's not 80 kilometers, it's not 20 milliseconds. It seems like numbers that might be right, so that sort of passes a really loose sanity check. Okay, so the key with problems like these is just to get plenty of practice with them. Both with the rearranging the formula aspect of it and solving the things, and also with extracting out the essential information from word problems. So don't forget that when you're translating a word problem, first make sure you define where your zero is and which way is your positive direction. So set up your axis. You then need to figure out which quantities you have and make sure that you give them plus or negative signs depending on which direction they're pointing in. So once you've set up your axis, make sure that a positive velocity corresponds to motion along it in the positive direction, etc., etc. Then once you've chosen your formula, rearrange it before you insert any numerical values and only round your results at the very end. Okay, so in this video, we've actually done quite a lot. We derived the main two kinematic equations and then mentioned that there are actually 3 other ones that you can find for yourself, should you so desire. And then we learned how we can apply them to a physical scenario, often specified as some kind of word problem. Now the key assumption that we need to remember is that kinematic equations apply when there is an interval of time with constant acceleration. That can also include zero acceleration. It'll just take a whole lot of terms out of the equations. But so long as your acceleration is constant or close to, then you can use the kinematic equations to get useful information. Okay, I think that's enough for this video. We'll catch you in the next one. Ka kite anō.